Halloween message in case I forget it next week.
Okay, any questions? Any questions? All right, so what we have done is we've talked about generalized tensors, right? And I defined this quantity. This is, more than anything else, it's just handy. It's not, we know how to move forward without this notation. Dx mu dx. Okay, so the next result is that, again, lack of a better name, I'm just calling it theorem. It's that ds squared. Oh, by the way, it is really ds squared because you have these two things. But I'm going to write it as just ds squared. It is not s squared and then d. It's just ds squared. And it really doesn't mean anything, it's just notation. Is invariant. And you know what that sort of means, but if you don't, in the proof it will be made clear. So what I'm going to do is I'm going to start with some coordinate system, y. And then write this in the x coordinate system, and you will see it looks exactly, the expression looks exactly the same. So you know now how tensors transform. So this g mu nu y can be thought of as d dx mu, y mu x alpha dx beta dy nu g alpha beta in the x coordinate system. That is how this guy transforms, right? And then what is dy mu? Well, I wrote that last time. So it is mu. Oh gosh, I need some other. Let me use sigma, and then I have dx sigma and dy nu dx lambda dx lambda. This is how these tensors transform. So this is g, and this is in terms of dx sigma, and so the three terms here are the three terms here. It really, all you have to do is to figure out which is it x on the top or y on the top. That's it. Get that clear in your head, okay? So when I write on the board, it might look clear if I'm right, just because it's just listed on the board, but you have to work a little hard to keep track of all of this. You can walk to the front.
Yeah, this might be already paused for you.
But see, then what I'm going to do is look at these two. We talked about this last time. They're just inverse. I don't know why I started early. Did I start like 2 minutes early?
Yes.
I guess I was eager to get started.
Hey, excited.
Does that mean we get to leave earlier?
No.
There's no law of conservation of time. So this, you will see, is, good try though, alpha sigma. And these two, tell me what that is?
Ask it one more time.
So I told you that these two, because they're inverse matrices, this becomes delta, Kronecker delta, alpha, sigma. So these two are also inverse matrices.
Is this beta lambda?
Beta lambda.
Yeah.
Beta lambda. And then let me just write alpha beta. This is an x coordinate system. Dx sigma, dx lambda. And then I can give up one for the other. So in particular, I can do alpha, and it becomes a sigma. And if I do that, I would get G sigma, exactly the same way I get G lambda, dx sigma, dx lambda. And this is in the x coordinate system. And this is sort of what I mean by it. I just wrote that down as a sentence. What I meant by an invariant is if you take this in the y coordinate system and convert it to x coordinate system, this is x over here, the expression looks exactly the same. So when you want to pick a coordinate system, you don't have to worry about which coordinate system you are in. The expression looks exactly the same. Is that clear? Okay. So we've talked about generalized coordinates, and also we talked about how tensors transform in generalized coordinates. And let me just pick a tensor in say y coordinate system. Tell me how in the x coordinate system, tell me the two matrices that go. To do the tensor transformation?
In the x coordinate system?
Yeah, you're starting with x coordinate system, and then you're ending up with y coordinate system. So let me remind you one more time. So when I do this, you have to fight it every single time till you get it clear in your head. But let me go through the mnemonic one more time. First of all, I would create two of these. Okay? And this is mu in the y coordinate system, right? So I would put y mu. This is mu upstairs. So, I put y mu, because these are the y's. So I put y mu, y mu. Then you know it has to be x. Well, if it has to be x, this is lower alpha, alpha, upper lambda, lambda. So that's the trick to make you remember, right? So we know how tensors transform. In particular, we've talked about how when you turn on gravity, we're just going to call it G mu nu. Yeah? Because eta mu nu is simply reserved for -1, 1, 1, 1, at least in a Cartesian-like coordinate system. Yeah? Now, again, everything we have done and everything we want to do is designed for space-time, 4-dimensional objects. But this is much more powerful. Tensors can exist in all kinds of objects, right? But it has to have a geometric shape, a geometric structure to it. Examples of things, these are called differentiable manifolds. So you can put these smooth differentiable tensors on any differentiable manifold. And you can also put possibly, at this moment possibly, turns out you can put a metric of your choice on any space, any manifold. It may not be a very useful metric, but gosh, you can put a metric. Now, examples of manifolds that's other than space-time, the surface of a sphere is a 2-dimensional manifold. You can do tensor calculus. We're not going to, but I should say these things exist. Surface of a sphere is a 2-dimensional manifold. They could have, unusual shape. For example, a torus, the surface of a donut, is also a 2-dimensional manifold. Because if you look at, it's a surface, so it's 2-dimensional. Klein bottle is a 2-dimensional manifold. R3 XYZ is a 3-dimensional manifold. Minkowski spacetime is a 4-dimensional manifold. But gosh, those are the intuitive, clear ones, and there's a whole list of them. You can take a hyperbola and rotate it. That becomes a 2-dimensional manifold. There are other complicated manifolds. We talked about SO3 as the group set of all rotation matrices. Turns out there's a manifold structure to it. You're going, well, how do you put coordinates on a matrix? Well, yeah, it's not difficult. I just don't want to spend a whole lecture doing it. Yeah. So there's a wide class of objects you can put a manifold kind of a structure. By that I mean you can also set up then tensors and do tensor calculus like we're about to. You can even put a metric. So as a simple case, I want you to consider, so in general, let me mention two, three terms. They're called differentiable manifolds. And suppose you put a metric tensor. Differential manifold or differential? Differential. So, and then you put a metric structure. Okay? Now suppose the metric structure is such that Gx x. This is a short form for what? Yeah? Suppose this is always greater than or equal to 0. It's like the length squared of a vector. Typically, outside of relativity, length squared is always greater than or equal to 0. It's in fact 0 if it is a 0 vector. If that's the case, we call it a Riemannian manifold. This is like R3, and we talk about R3. Suppose you have vectors say, or there are the x such that Gx x is less than 0. Do we have them in relativity? Do we? Why are you guys quiet? Yes or no?
Is it analogous to like time-like, space-like?
It's a time-like vector, right? Suppose if you have in a space vectors that have negative length squared, then they're called a semi-Riemannian manifold. Okay, that is 1, that's 2, but it's so 3. And this is special to us. Suppose in an orthonormal plane, we have exactly one time-like vector, or one vector with less than one vector with say one vector x with Gx x less than 0, and others y with, this is just bad, we have exactly one vector, then we have, this is just words, definition, we have a Lorentz So if you have all vectors whose inner, with, when you find its length square, I'm just going to call it length square. What I mean is like this quantity. If it is positive semi-definite, means greater than or equal to 0, then we say it's a Riemannian manifold. This is like our Euclidean space. Suppose you have vectors with negative length, like in special relativity, we call it a semi-Riemannian. Now, you could have many dimensions of vectors with negative length. But one is special of all of that with exactly one time direction. Those kind of manifolds are called Lorentz manifold. So relativity is a study of, can also be a study of Lorentz manifold. Because if you have an orthonormal basis, you will have exactly one time-like vector and three space-like vectors. Okay. All right. So in R3, following what I just mentioned, and these are some problems that you'll be doing. I'm just setting it up for those problems. One would typically see this. So I'm going to compare this with this notation. So if you see this, what you should understand from that is gxx equals gyy equals gzz equals 1, and gxy equals gxz equals gyz equals 0. Yeah, there are no cross terms. So it is a metric tensor with these being the entries. Now remember, I didn't give gyx. Why didn't I give gyx? Because a metric tensor that applies to these categories should have two important qualities about it. One in particular, it should be symmetric. Right? What does that mean? Gxy should be gyx. Because A dot B, at the end of the day, should be B dot A. It would be weird to have an order to it. It doesn't serve our purpose in relativity. Yeah? I don't know if one could conceive such a structure. And the other thing that is very important to us is that a metric tensor should be non-degenerate. There are many ways to look at that. It just means, one way to think of it is determinant of G should be not equal to 0. And you'll find this to be the case. So again, if you see this, can you translate to this? Good. One of the homework problems is I will ask you to show in spherical coordinates the same ds squared can be written as dr squared plus r squared d theta squared plus sine squared theta d phi squared. You'll be doing this. Again, really, d phi squared is short for d phi d phi, which I mentioned can be used to put tangent vectors in there. So in this case, tell me what the non-zero components of the metric are. If you see, so what I'm saying is if you take this metric and then you do the coordinate transformation of a spherical coordinate system. You will do that. When you do that, this guy ends up being that. Yeah? Okay. Now suppose you do that, and this is the answer. Tell me the coefficients of the metric. The non-zero ones, at least. So, what are the spherical coordinate systems? R, theta, phi. So, what could be the components? G, R, theta, G, R, phi. Then you can have G, theta, theta, G, theta, phi. Then you can have G, phi, phi. In 3 dimensions, I'll have only 6 of them. Because the other ones, for example, G R theta should be the same as G theta R. Tell me the values of these guys.
One.
Tell me, oh good, this is
One.
1. Tell me this guy.
0.
0.
And then 0.
0.
1.
Nope.
Wait, G theta theta?
Yeah. Be careful. You're going to hit me for correcting me. Can we agree this is 0?
Yeah.
With that in mind, what's this?
Sine squared of theta.
Sounds good.
Oh, R squared, sine squared
theta.
theta.
That's what it is.
Yeah, that's exactly what this tensor is. Now, suppose there's a trick to it. Suppose I want the metric of a sphere. What do you think that is? I can look at this and just write that down. Sphere of radius r. Oh, let's even make it more interesting. Unit sphere. What is a sphere? Correct. That's a hand gesture. Say it in words.
A sphere is a sphere.
Three-dimensional
It's like when you take a
Three-dimensional
circle and you just
circle.
rotate.
Is it
Correct.
a three-dimensional circle?
All right. So I'm not going to say it in words either, but on a sphere, r equals constant. The radius is a constant.
Yeah.
But when I say unit sphere, what do I mean?
It's 1.
What is 1?
R.
R is 1. So suppose I have a surface with r being 1. What would that metric look like, or the invariant look like? This is what you'd be staring at, and then you'd be giving me an answer. Gracie, I know you can do it. You into it.
Would it be,
Go for it. It could be wrong. I don't care.
would the dr squared go to 0 because it's a constant?
Correct.
And then we'd have d theta squared plus sine squared theta d phi squared?
What did I say? My faith in you has been justified
This time.
this time.
Because Jackson's better.
That this is the metric of a sphere. Now, that's odd that this is a metric of a sphere. Why would a sphere has no special points, correct? No, you cannot distinguish one point from the other. Why is sine squared theta showing up over here? Because that changes with theta. That's odd, right? It is not. It is only because we chose the coordinate system where z-axis is the where theta is measured from the z-axis. Yeah. If we chose a different z-axis, it'll show the metric will end up being exactly the same. And those things are part of the homework problems I'll assign. And you will see that it is true that there appears to be a coordinate dependence, but that is false. This is exactly the metric of the sphere. In any coordinate system, in any, you rotate the Cartesian coordinate system, it'll look like this. And therefore, it is just a coordinate feature. This is, in fact, the metric of a sphere, and no points of a sphere are special. It will be revealed through a series of simple exercises in your homework. Therefore, anything that has this and only this as the angular dependence will have a nice property. It would be spherically symmetric. I use that word, it's an old Jedi mind trick. I'm instilling those words and features so that, 2 days from now, 3 days from now, when we study Schwarzschild black holes, you'll go, oh, Schwarzschild, it'll be a solution of a metric, a space-time that is spherically symmetric, like a non-rotating star that may have collapsed. If it is spherically symmetric, guess what the angular part of the metric will look like? Yeah? So just, you can intuit general relativity, at least that of a Schwarzschild spacetime. And that's exactly what we'll do to get started. Okay, good. Okay, now comes the fun part. No, fun doesn't mean not fun.
You just started talking about Jedi stuff, and then you didn't say this is where the fun begins?
Should I have?
Yes.
This is, well, I thought fun began a long time ago.
Day one.
Day one.
Hasn't stopped since.
So this is what we're going to do. We're going to use the implications of, I should say implications. What's EP? Equivalence principle.
Oh, yes.
What does the equivalence principle say? Gravity is not a thing. Right?
Give us a second to try.
Like, I looked right to the page.
Yeah, you're flipping. No, that's no good. It should be in your brain. Yeah? Every point locally, if you accelerate, if you fall freely with gravity, you don't detect the feature of gravity. Okay. So we will have this in mind, an object just falling freely in a gravitational field. So these things will continue to, there'll be like an x mu, some coordinate system. We use x mu as a function of s, and u mu will be, as usual, dx mu d tau of s. Well, you go, well, what is this tau? Well, c tau equals exactly like before. I mean, the only difference is going to be this. What's the difference? Eta has been replaced with G. That's it. So we know how to take proper time and find this. And as usual, G mu mu, U mu mu is minus C squared. In short, we usually write this as minus C squared. So let's keep this in mind. And along the path of a particle, we consider one point P. Exactly at that point, you can immediately jump using the equivalence principle to a coordinate system that is inertial. Because the equivalence principle says you can just wish away gravity if you do the right thing. So we will construct an inertial coordinate system psi mu. By psi mu, I mean this is, of course, it's a 4-tuple, psi 0, psi 1, psi 2, psi 3. Such that at P, only at P, at one point at a time, we're calling that point P. G mu nu evaluated in the coordinate system psi, when evaluated at the point P, this is, at that point, there's no gravity, so the metric looks like what? Minkowski metric. There exists a coordinate system. Yeah? So this is the, there exists. It's a free-falling coordinate system. It's like the camera inside the spaceship, where things are just hovering as if there's no gravity. Yeah? Furthermore, if I take the derivative, I'll tell you why, of this guy, and then evaluate it at P, just like special relativity, this doesn't depend on space and time, so I'll get 0. Why do we need this? Physical theories are theories with two derivatives, right? What is force equal to? F equals?
Mass times acceleration.
Mass times acceleration. What is acceleration?
The second derivative.
Second derivative. To solve a second order differential equation, what are the two things you need?
Starting point.
Starting point. Good.
And point 2.
Well, that is a very complicated thing. Maybe that's true, huh? That's Lagrangian mechanics. We won't do that. But what else do you need? I'm going to draw it out of you. You guys should know this.
I feel like it's super obvious.
It is super obvious. You need two things. Initial position and initial velocity. Einstein's equation is also a second derivative equation, right? So you need two things. So these are the two things that we need, and we relegate the existence of such a coordinate system to the equivalence principle. We translate it to, this is what it means. Okay? Now, I want to tell you what it does not mean. Any questions? So, let me call this temporarily, let me just call this 1, let me call this 2. 2 implies the following. In any other coordinate system, x mu dx mu of the same object. Oh, let me put different index. Dx alpha g mu nu of psi is 0. Not just an inertial, but any other coordinate system. Well, that's easy to see. Here's the proof. D dx alpha g mu nu of psi is equal to G mu nu of psi d psi beta d psi beta d. But this guy is 0. Right? So this continues to be 0. Because this is just a multiplication of a 0 matrix. So that's what it means. Let me make it very clear what it doesn't mean. And tell me, as I prove this, what's the difference? This does not mean. What's the difference between this and that?
So, like, coordinate system?
Speak up, you're right.
Like
Let's be.
coordinate system? Like the x versus the psi?
Correct. So this is the metric in the psi coordinate system. Okay, so let me make that very clear. Metric in the psi coordinate system. What is this?
The metric in the x coordinate system?
Metric in the x coordinate system. It does not mean that the derivative in the x coordinate system is 0. As a matter of fact, when I see this, it's just jarring. Okay, to be very clear, this is the case. But I said it does not mean. Now, why wouldn't it imply? Why wouldn't that imply this?
Is it a different inertial frame?
But how can I show that mathematically? You know, we show that if I take the derivative using any coordinate system, it is 0.
Is it because you're having to change coordinate systems?
Correct, but how would that carry through?
You're taking the derivative of the psi system with respect to x or something?
True, but so that is true. How can I show that that is not equal to this?
Just because you don't have to change it at all?
Change what?
The coordinate system.
Let me clarify. It's a subtle point. Note, the reason why this is not true is G mu nu in the x coordinate system is G alpha beta in the psi coordinate system. And then I have x nu, psi alpha, psi beta. So if I take the derivative of this, I don't get 0 because these two guys have cropped up. The derivative of that is 0. Okay? It's a subtle point. Just visit that over and over again. So this is not the case, that is the case. And they differ by these guys. Correct? Are we good? Yes.
So the derivative of psi is 0? Well, like the derivative with respect to psi is 0 always?
Well, derivative in the inertial, the derivative of the metric in the coordinate that is inertial at that particular point. Oh, remember, this is only at one point.
So it could be x at any other point if it was taken.
Oh, okay.
Yeah, but this doesn't have to be 0 at any other point other than P. Because at a point P, I have created an inertial coordinate system. And locally, immediately at that instant, at that point in space and time, it's like gravity doesn't exist.
And you just happen to label it psi.
We call that psi. Yeah. That initial inertial coordinate system, which is only inertial at a point P, is what we're calling psi. Okay? So this is 0, this is not zero, even at the point P. This is also 0, only at the point P. Are we good? Zach? Okay. Fine. That gives us an immediate result. The determinant of the metric, even in general relativity, is not 0. Because determinant of g mu nu is what? Any coordinate x is equal to determinant of d psi alpha dx mu, because the product of the determinant is the determinant of product. And this, of course, is theta. I know this is not 0 because it's -1. Why are these guys not 0? So I'm going to write this as not equal to 0, not equal to 0, therefore this is not equal to 0. But why are they not equal to 0? Look at your notes. Perhaps even from last lecture or the lecture before that, maybe last lecture. What would make that, this matrix, if you will, and I say matrix because it has 2 indices, its determinant is not 0. Zachary. Tucker. Psi is an inertial coordinate system. X is just any other coordinate system. For us, the fact that in this particular case, psi is a coordinate system is not, inertial coordinate system is not important. If you have psi to be an inertial coordinate system, psi to be any coordinate system, and then x to be any other coordinate system, I claim that this determinant is not 0. My question to you is why?
Does it have anything to do with the indices, or is it just a broader scope?
Much broader, much broader. We talked about a theorem, and I said this is sort of the heart of the analysis of everything in, of many things in relativity, or different theory of differentiable manifolds. It's called differential geometry. This is because of the inverse function theorem. The determinant of the transformation matrix. Inverse function theorem. Right? It says the determinant of the transformation metric cannot be 0. If it is 0, it's not a valid coordinate system. This is, of course, at the point P, but P can be any arbitrary point, and at any arbitrary point you can take an inertial coordinate system. Let me quickly end with one more result. If the determinant of a matrix is not equal to 0, what is true? The previous corollary implies that G mu inverse exists. This is true from linear algebra. If the determinant of a matrix is not 0, its inverse exists. Notation? What do you think the notation would be?
Is it G up means that?
Yep. So, what I'm trying to say here is G mu alpha is delta mu alpha. Now I can raise and lower any tensor using G and G inverse. For example, I can do this. Raising and lowering. What is A mu? It's G mu alpha, A alpha. Correct? What is A mu? Well, let's get a tensor with 2 indices. What do I do? Oh, the other way around. So on and so forth. You can raise and lower all indices using my inverse. Any questions?